A very warm welcome from my side to the presentation Industrial Pellet 3D Printing. My name is Nicolai Lammert and I'm the head of Additive Manufacturing at the Yizumi Germany GmbH. The title Industrial Pellet 3D Printing means that we want to offer our customers or our partners a technology in 3D printing which is competitive from an economic but also from a technical point of view with injection molding processes, for example. What will we start with? At least we will start with the Space A technology with a basic approach. Afterwards we will go along with economic calculation. Then we will see that a best practice design is for sure the best situation to start with additive manufacturing. And at the end I want to show you our Space A machine series. If we start with the basic approach of our technology, we will see that we ever use a single screw extruder which is able to process thermoplastic materials. This single screw extruder will ever mount it on a positioning system. In terms of our standard machines, it is a robot system. And for sure, to have a good pre-treatment of the material, we ever offer our customers, our partners, a dryer and a complete supply chain for the thermoplastic materials. For sure, you can also order or get a single screw extruder from us, only to be implemented in automation style of your use. What is the basic situation now? At least we will start with the melting strand, and we put that melt strand on a substrate. And due to the fact that we are having a solidificating strand and we are running with a new melt strand over it, we can build up a three-dimensional part like we see in this video. At least that is a presentation of the case show of the Formnext 2018, where we produce that parts you can see here every 35 minutes in a completely automatic process chain. So that means we produce a part, the piece carrier supply chain here will put the part outside the manufacturing cell, and we will start automatically with the new part. What you can see here on the video, that we have a trade fair manufacturing cell. That means our robot is way too big for that part. For sure, it's really sensible to reduce the robot size according to the part size, and then you can achieve economic situation. But what is really good to see here is the automatic approach and what you can do in terms of scalability, but also in terms of line integration. If we go forward, we can see that our situation is sometimes the productive technology. We want to achieve the line integration. We want to be able to process different thermoplastic materials of your knowledge. So you can put every granule you have in mind inside of our extruder, and that's most of all not the problem. We can extrude the most materials, but afterwards you have to check if it's possible to print that material to a three-dimensional part. And what's for us as machine suppliers really important is that we can support you with a technology which is simple, which is fast, and at least moldless to be competitive in terms of injection molding. Right now I want to go forward with the economic calculation, and we'll start with the housing structure. Only as an example, we also see that in the video. With the boundary conditions you see here, we have more or less the possibility to produce that part in 2.58 euro per part. So that is more or less really a competitive price if we go ahead with the comparison we see here in that slide. That means in terms of existing additive manufacturing processes, or at least also in terms compared to injection molding. For sure, compared to injection molding, we are only competitive in that range of 10,000 parts per year. If we want to produce a higher lot size, since something like 100,000 parts per year, then perhaps the deadline or the break-even is not on the side for additive manufacturing, but injection molding is the best choice for that. But you can also see, if we only want to produce 10,000 parts per year of that part design, additive manufacturing or our additive manufacturing technology is a quite good solution to fulfill that job in an economic way. If we calculate right now different possibilities, different examples compared to that boundary conditions like throughput or machine size, machine costs, we can get such a diagram. I want to explain it a little bit more. So on the left side we have the part costs, euro per kg, and on the right side, on the bottom, we have the annual throughput against machine costs ratio. At least that's more or less the economic ratio to perhaps get a handleable value for the machine capabilities. That means if we have a expensive machine with a high throughput, is as good as a cheap machine with a low throughput. But what we see in that diagram mainly is that the most important effect after a really slow technology is that we have to use material with low costs. So we see here 120 euro per kg, 25 euro per kg, or 5 euro per kg, and only if we're using 5 euro per kg material, so a similar material to injection molding, we are able to meet something like the injection molding reference line. That's for us that red line here you see in the picture. That means if I use a 5 euro per kg material in injection molding, we have to calculate with 50% material cost share. And that means our part has a cost of 10 euro per kg. And to fly under this red line, we really have to use a granule material. That means the main cost effect is mostly the material costs. Afterwards, we have the throughput and the machine costs. For sure, you have a good throughput, a high throughput for less machine costs, then you have a good economic ratio here. And the last one, but for sure it's really important, is the part design, because if you have double the time due to a bad part design, then you have double the cost, or mostly double the cost because of the amortization period. To go forward, we can now sum up that the additive manufacturing technology, which is able to be competitive in terms of injection molding or compared to injection molding, must be an additive manufacturing technology which uses granules. And that is our basic approach here. Right now I want to go a little bit deeper in the field of part design. So why is part design here on the fourth level and why it's here so important for us too? I want to explain it more or less on this slide. You can see on the left side we have a really nice part design for our technology, because we are just moving around and around with our melt strand. On the right side we have a really complicated part design, and it's more like a bionic structure for SLS perhaps. And what you see, and what is perhaps the main point to get the magnitude shift or to get the need or the demand for new technology, is that we have on the left side approximately 3 euro for some part like that, and we have competitive technologies like SLS or multi-jet fusion. They're producing it with really higher costs and with a magnitude shift. And on the right side we see a part from the industry with a required part cost of approximately 80 euro. That means, and if we compare that, it will be not possible to produce such a part, even it's not technically possible with the powder bed technologies, with that technologies only because of the price. Our technology, the Space A additive manufacturing technology with thermoplastic use, is able to produce that part for roughly 78 euro. Only if we look at the weight of 5 kg. For sure, if we want to produce a part like that here on the right side, it will be cost something like 800 euro even with our technology or with the screw-based additive manufacturing technology, because of that non-productive times. That means we don't only produce or applicate 5 kg, we are also driving around the world without printing any material. So you can see here the little bars, and you have a lot of traveling movements which are without any melt strand application. And that means you lost a lot of time. It's more or less like open the mold, close the mold, something like 24 times, and only at the 26th cycle you have a part. So it doesn't make sense from an efficiency point of view. And if you compare that to possibilities in designing, we will see, okay, we have to design that perhaps more like sheets, and we have to design in a different way. So not the bionic structures like we see in that picture, but we have to design perhaps our parts a little bit different. And for that, I want to give you a short overview about a design study we made together with the AZL in Aachen and Acroplastic. We have more or less a bicycle frame here, and it's upside down, and you really can see that we print the bicycle frame without any non-productive times, because it's a waste mode design. So also part of our waste mode collection, but we can produce it just printing in a row. So we have ever a spiral here inside of the chem code, and we just printing, and we never stop applicating material in the part. And with that technology, we can reduce our waste time, or we can increase our production efficiency to 100%. And on the other side, we can use different design aspects to get more mechanical properties inside of the part. If we compare that with the original aluminum part with a weight of 1.2 kg roughly, we can reduce the part weight of around 50%. And that is an aspect which we can use by different design aspects which we can implement in that bicycle frame design. Because additive manufacturing, in terms also our melt strand deposition technology, enables us to integrate hollow structures to increase the stiffness of the part, or we can use that technology to produce really thick walls, really thick wall thicknesses. More than 10 millimeters are possible here. And if you imagine what is possible with a 10 millimeter polyamide carbon fiber filled material here, you can imagine how strong and how stiff that angles are at the end. And we can just produce that thick wall thicknesses or the hollow structures without any cycle time effect. So that is really an advantage of the technology, but we have to design according to that possibilities. And for sure, we also build it up together with the AZL, like I mentioned. And it's also possible to drive with that little bike. At least I want to point out a few advantages of that technology based off of robotics and using a screw-based additive manufacturing process. The first point is the scalability. So it's really easy to scale or to reduce the cost of such a system in terms of the part size. If you have only a small part, you can also use a really small robot at the end. For that, we use own developed extruder, a lightweight extruder. It has something around a weight of 7.5 kg. And due to that, it's possible to mount it on a wide range of different robotics or positioning systems. That extruder enables a high productivity because we can process with some plastic materials, we can process granules, we can bring shearing inside of the material and plasticize a lot of material in a short time. Due to the robotic approach, we have a high potential of automation. That means we have a good line integration, which is possible here. We have also the possibility of material diversity, can put every granule inside of it that you have in mind. What we right now see in our main approach is that we have a print module and have a platform module. So we have a good flexibility to our customers. You can forklift it, you can crane it, and we have a good machine software over it to give you more or less the situation that you can handle it as a standard injection molding machine or a standard plastic processing machine. Last but not least, I want to present our modulus platform strategy. We have not only our big machine sizes with print module and platform module, we have also our small machine sizes with different dimensions and scalabilities. And you can imagine that we have good pricing approach right now here because it's easier for us to handle it. We are also working on the terms of metal plastic hybrid parts, and you can ever ask us and get in contact with us to get some information about that. With that sentence, I want to say thank you and wish you a nice day.